Welcome back, welcome back. Time for the challenge problems. These are nice and fun and sciencey. Alright, 9.63. It's on page 366. Feel free to join me. You mix 0.1 moles of PCl5 with 0.05 moles of PCl3 and 0.05 moles of Cl2 in a 1 liter container. Alright, so after reading that, we're also given, we're given the equation, so it's PCl5, reversible reaction, is a PCl3 and then a Cl2, I believe. Let me check on that. Yes, it's Cl2. And it also tells us that Kc equals 4.2 times 10 to the negative second, which can also be written as 0.042. These are the same thing. Like this, they're reversible. So, part A asks, is the reaction at equilibrium? So this right here, 0.042 of the Kc, that is at equilibrium. So we're gonna plug these numbers into Kc to see if it actually is at equilibrium. So let's go for that. So down here, I'm gonna separate all this out. That's over there, this is over here. So we have Kc. Let's plug in what we have. It tells us PCl5 is 0.1 mole. Product over reactant, sorry, 0.1 on the bottom, my bad. And then on top it's 0.05, yeah, they're both the same. It's 0.05. Alright, let's do the math. So 0.05 times 0.05 is 0.0025. Let's divide that by 0.1. And we're given 0.025. Alright, so this is the actual Kc, and this is the Kc that it requires to be at equilibrium. So is this number the same as this number? I think any second grader could tell us that these numbers are not the same. In fact, this number is much smaller. And that's where part B comes in. So it tells us, it asks us, since it's not equilibrium, will the reaction proceed in the forward or reverse direction? Alright, so basically the rule is, if the Kc is smaller than this, it'll proceed in the forward direction. There's not really an example I can do for that, just know that. If your number is smaller, it goes forward. If this was, let's say, 0.85, boom, nice. 0.85, it would go backwards in the reverse direction. Just know that. That's the rule on that. There you go. That's one challenge problem knocked out. According to Bryson, this next problem I'm going to do is the hardest in the chapter. So hopefully once we get this figured out, we'll be good. Stay on the wall. Freaking crappy duct tape. Sorry, lost my cool there. Alright, so 9.64. Uh-oh. Facebook. Actually, let's get 9.64. 64 is the same thing. 9.65. Consider the following reaction. It's the same thing as last time, so PCl5, PCl3, and Cl2. No big deal. That's the reaction. It asks us, write the equilibrium constant expression for the reaction. So let's just simply do Kc. This is easy. Part A, Kc equals product over reactants of PCl3 plus Cl2. Let me make sure that Facebook vibration on my phone didn't. Nope, we're good. Okay. Sorry about that. Freaking social life, man. It sucks. PCl5. Alright, so boom, part A, knocked out. No big deal. You've done this like 6 times now. It's easy. Here's the hard part. So let's read through this together. I'll go slowly for this. Initially, 0.6 moles of PCl5 is placed in a 1 liter flask. 1 liter flask doesn't matter. Ignore it. At equilibrium, there is 0.16 moles of PCl3 in the flask. What are the equilibrium concentrations of the PCl5 and Cl? Alright, so it tells us, let's erase that actually. So we're given that 0.6 moles of PCl5, so let's plug these things in. 0.6 moles reacts with 0.16, is that what it said? 0.16 moles of PCl3. PCl3 plus, alright, now this is where it gets complicated. How do we know how many moles of PCl2 there are? So, basically, I'm just going to put that 0 right here to make it easier. Alright, that's a 0, okay? Just take more on it, that's 0. That's 0.60. Just keep it double digits, make things easier. So I'm going to draw out, actually, and I'm just going to tell the answer and then explain. So it's CL2 is also 0.16, so the same thing. And that's because PCl5 is 1 mole turning into these two things. So basically, it's all going to be the same, so all the numbers have to add up. So let me draw out why. So PCl5 is a P with 1, 2, 3, 4, 5, Cl, 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 Cl. This right here is the actual electron, or sorry, just the actual diagram of that, drawn out in sciencey ways. And it turns into a PCl3, which is P, 1, 2, 3, Cl, 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 and this is 0.16, right? And then it's just got 2 Cl's left over, so it'd also be down here, it'd be Cl and Cl. This is also 0.16 because they're breaking apart from the same thing. So I mean, like, if you cut this in half, it'd still be same. So that's why it's also 0.16. I realize you might have had to rotate your head this way to see that, so my apologies. I'm writing on a freaking huge board here. So, what are the equilibrium concentrations of the PCl5 and the Cl2? So since 0.60 is reacting and turning into this, you gotta subtract 0.16 from this, because it's turning into this. So it'd be actually 0.44. And I got that from subtracting the 0.16. 60 minus 16 is 44. So PCl5 equals 0.44, and then the Cl2, because of what I drew over here, is 0.16. There you go, that's it. Let me make sure that I formatted that correctly, and let me check in the book. Yep, okay. So now it tells us, or it asks us, what is the value of the equilibrium constant Kc for the reaction? Alright, so now we're just going to plug in what we have. So it's more Kc crap. Here we go. Products over reactants. So these are both 0.16, so 0.16 times 0.16 divided by 0.44. Sorry. Let's do the math on that one. 0.16 times 0.16, 0.0256 divided by 0.44 is 0.058, and that is correct. So Kc equals 0.058. Boom, no big deal. Let's see here. If 0.20 moles of Cl2 is added to the equilibrium mixture, will the concentration of PCl5 increase or decrease? So this is just like what I did a few problems ago. You add Cl2, will this increase or decrease? So if you add some of this side of the reaction has to go faster to shed off some of that extra Cl2. So it'll actually make this more concentrated because it's happening quicker over here. Like more and more reacts quicker, so the concentration of PCl5 becomes more concentrated. That is that challenge problem explained. I always wear this stupid watch so I can look at it right before I start the video and then know how long the video is so I can stop around 10 minutes. I have no idea how long this video is. Hopefully we're almost done. I don't know. 66, same thing. 67, same thing. 68, same thing, same thing. It's all pretty much the same thing. Here we go. This will be a good one. Here we go. 9.69. Alright, this is a long one. C solid plus H2O gas. So this is gaseous water. Plus 31 kcal hate that word for some reason. Kcal. Ugh. I'm going to keep the products down here. So reversible reaction is CO gas plus H2 gas. All right, so I'm going to explain something here called, I'm going to call it the rules of heterogeneous reactions. There you go. The rules of heterogeneous reactions. Yes, came up with that on the spot. All right, so remember in the very, very first video, I think the first problem I actually did was heterogeneous versus homogeneous. Homogeneous is they're all the same. Oh, looky there. This is heterogeneous because it's a solid. And that means when calculating the Kc, you do not include this. So just basically pretend it's not even there. Just want you to know that. All right, so I'm going to go through a list of things. There's actually 1, 2, 3, 4, 5, 6, 7 things that happen, and I'll tell you the effects on the reaction. So pause the video right now and go through these, see if you can answer them on your own, and then come back here and I'll give you the answers. I'm going to explain why. All right, so what happens if we add more H2? All right, you added more H2, so there's more H2. So remember, if it's added, it needs to shed it away as quickly as it can. So it's going to increase. This is going to increase in speed. So that means this side becomes more concentrated. So the equilibrium constant goes in the reverse direction because it's going this way. Increase the temperature of the reaction. This is endothermic because it's happening on the left side. So if you increase the temperature, it needs to, yes. So increase temperature, so you bring it up to 45 degrees. 45 kcal, good lord. I hate that freaking word. Anyway, if you increase it up to 45 kcal, this needs to shed away some of the extra heat. So it's going to... See, my brain messes up on these temperature things. If you have an endothermic reaction and you increase T, yeah, it'll shift this way. Because it has to shed away some of that extra temperature to bring it back down to the regular temperature of 31 degrees. Easy, no problem. Next up it says increase the volume of the container. Alright, so if you increase the volume of the container for everything, nothing will change because this is both gas, this is gas, so everything should remain the same. I'm going to check that really quickly just to make sure. I was wrong, it increases. Let's see here. Oh, I'm sorry. The question asks us the equilibrium concentration of CO. So what happens to the concentration of this? My bad. I was telling you what actually, just whatever happens. Okay, so let me restart really quickly. Add more H2. It'll decrease the concentration of this because with the H2 getting bigger, it has to shed off some of that. So this side speeds up to bring more in this direction. So this is going to get less concentrated. B, increases temperature, like before. Increased temperature so it shifts this way, which means the concentration of this will increase because it's going in favor of the products. That is correct. C, it says increase the volume of the container. So if they're hitting less, there's more gases over here, so it's going to be hitting less. So it will become more concentrated. Yes, more concentrated. Decrease the volume of the container will decrease the concentration of CO2 because they're reacting more, which means that the molecules will be hitting more, so it speeds up and shifts this way, which means this loses its concentration. Adding a catalyst. Adding a catalyst should do nothing because here's a chart for activation energy. You remember this. This right here is the energy required to start the reaction. What a catalyst does is brings this thing down to here, so it can happen earlier. That affects how much energy is required to start the reaction, but it doesn't actually change the concentration of CO. So there's no change. No change on that one. Decrease the temperature of the reaction. Oh, sorry, looking at the wrong thing. Oh, no, right. Decrease the temperature of the reaction. That will decrease because, or decrease this concentration because if you lower this down to, let's say, 29 kcal, then this needs to gain heat. And to gain heat, this has to speed up. So if this is sped up and shifting in this direction, it's going to become less concentrated over here. Remove some H2O. Let's see, removing H2O. So you remove some of this, it goes down in amount. So that means that it needs to make up for this by adding more. And to add more, this is going to speed up, which shifts it this way. Which means that it'll decrease in concentration. Alright, that pretty much covers chapter 9 and all the hard problems in there. If you guys have any questions, just send me a text message. I'll upload more videos if you need them. I'll get to chapters 10, 8, all through 1 eventually. Over the holidays especially, I can knock those out. But thank you for watching. Appreciate it. And y'all have a great night. Or day.